People here. Wonderful. Cool. Yeah, I'm Benji. Let me hide these floating meeting panels. Yeah, good, good. Cool. So I'm going to be talking to you all about my PhD research, which is all about exploring chemical inhomogeneities in galaxies across cosmic time. So what I'm really trying to understand is galaxy evolution. And there's a few things that we do know about this. Let me shrink myself. Yeah. So we know that from these small fluctuations in the early universe, we have structure growth into the large cosmic web that we see today. And from this cosmic web, in its densest regions, we know that gas accretes and collapses to form stars in these systems called galaxies. So from this perspective, galaxy evolution is a solved problem. Obviously not. There's some few things that we still don't know that we're trying to get a handle on. Mainly the gas physics, or the gastrophysics, if you will. So we know that cold gas has to accrete into galaxies to fuel future generations of star formation, but it's still pretty unknown whether this happens preferentially on the outsides of the disk or in the middle regions, and whether it's smooth or if it happens in clumps. We also know that gas is driven out of the galaxy by like large-scale galactic outflows. But how metal rich should this gas be? How much of it escapes permanently and how much of it falls back in are all kind of like open questions in astronomy so far. I'm also interested in mergers. We know that mergers are really important for these large-scale drivers of galactic growth and evolution throughout the universe. And another thing that we know is important that we don't really understand is the role of feedback and turbulence. So when stars go off, they blow out a lot of material, which disrupts future generations of star formation and enriches the intergalactic medium. But every simulation has a different model for how this is supposed to work. So to kind of understand these small-scale baryonic physics that are kind of like driving galaxy evolution, I look at metals. And this is a really nice periodic table that's been prepared by the Astro 3D team, showing about how all of the elements in the universe came to be over cosmic time. I really like this plot, and you can spend a lot of time looking at it. But for the purpose of this talk, all you really need to know is that everything except for these first three, hydrogen, helium, or lithium, were formed in a star. And so by tracing where these elements are throughout a galaxy, we can learn a lot about where stars have been forming and where the products of star formation have been mixing into the interstellar medium of these galaxies. So to do that, I use integral field unit spectroscopy. So these IFUs are great. They're bundles of fiber optic cables that allow you to take spectra at every pixel of a galaxy at the same time. And with this, you get to construct pictures of galaxies that look like this. So at every X and Y location, you have an entire spectrum of colors that you can use to derive the metallicity at every single location of the galaxy. And with modern data in nearby systems, we're getting really incredible pictures of the chemical structure of these galaxies. So this is a picture of Muse. You can see that there's more metals on the middle, less metals on the outside. But there's also all of these details of like local metal-enriched or metal-poor regions that show us kind of like these signatures of like these small-scale astrophysical processes that are driving galaxy evolution. In addition to this really nearby stuff, I'm also interested in some of the new results coming out of James Webb. So this is a metallicity map that was recently published. It doesn't look as impressive. This is at redshift of 3, so it's pretty impressive. And you can see that there are like large-scale metal inhomogeneities in this galaxy as well that don't really fit with your simple metallicity gradient profile. So that's the kind of work that I'm interested in doing, is connecting this latest observational data to our theories about galactic formation and the ISM, both with this really high resolution data, redshift 0, with this data that's not so high resolution at around cosmic noon, and also for galaxies at further redshifts where we have no spatial resolution at all. And so I'll talk a bit about how that's going to work, but first, let's start with the most exciting data, the really nice, really high resolution stuff that we can see in the local universe. And the tool I've kind of been pioneering using to analyze this data is something called geostatistics. So probably wondering, what is geostatistics? Why have I never heard of it? It's not because I made it up. I would have named it something much cooler. Instead, it's a family of tools and techniques that was developed by a group of French mathematicians, notably Georges Matheron, in the 1960s and 50s, with the applications of sort of like taking a statistical approach to prospecting. So in the gold rush in South Africa, they were digging up a lot of gold over here, not much gold over there, trying to answer questions about like where to dig next, trying to construct 2D predictive models of the metallicity of the metal distribution rather. But if you replace metals with metallicity, replace a gold field with a galaxy, the math doesn't know. And so you can use this same family of tools and techniques to make insights into your galactic data. So how does it work? Basically, it's a hierarchical modeling framework. So the first thing we say is that the metallicity we observe at each location X isn't the true metallicity. There should be some observational error that sets it apart. And this isn't so new so far. We say that what we see is signal plus noise. The more novel split is where we say this true metallicity comes from two components. There's the mean metallicity that we'd expect it to be at each location, which comes from like the metallicity gradient model usually, but you can use other models. But then you say on top of that, you expect there to be some random fluctuations in metallicity that are present in your data that are not noise, that are signal. But basically, you don't expect the metallicity at each location to be exactly on the mean metallicity of the location. You expect some variance because star formation is a stochastic process. The turbulence that mixes the products of star formation is a stochastic process. And so you've got this stochastic component that's correlated over small scales that you're trying to characterize. So the game is to try to model these three things. If we can understand how we expect the noise to behave, the large scale trends, and these small scale fluctuations, then we can get a really nice predictive model of our galaxy that we can start comparing to theories. So the challenge here is how do we separate these small scale features from the noise in our data? This is a challenge, but luckily geostatistics has a tool that can help us in the semi-variogram. And this is something that allows us to separate spatially correlated and uncorrelated sources of scatter around a mean trend. Basically, it's a plot of the variance between pixels as a function of the separation between them. But rather than go into the maths, I prepared this more fun worked example. So up the top, we have 3 different random fields, and down the bottom, we have 3 different semi-variograms associated with each of them. So in this first random field, we just have white noise. There's no correlation between, no spatial correlation in this data at all. So if you look at the variance between any 2 pixels, it doesn't matter if they're separated by a small amount or a large amount, the variance is the same. And so what you get for the semi-variogram is just a flat line, constant variance at all separations. In this next panel, we have a more interesting correlated structure in our galaxy. So this time, if you look at 2 pixels that are right next to each other, the variance in the metallicity will be much lower than if you pick 2 pixels that are further apart. And so you get this plot of the variance increasing with separation. And this is a really informative plot because it tells you the physical size of the largest fluctuations in your data, and also the amount of power within these fluctuations as well, which are 2 like key characteristics of this kind of data field. In this third field, I've actually done something a bit cheeky, which is just add these 2 random fields together. And so now you've still got this correlated signal, but it's hidden by this white noise component. Luckily, when you add variance, it's an additive quantity. So when you look at the variance at each separation for this final graph, it's just going to be the variance at each separation for this graph, plus the variance at each separation for this graph. And so what happens when you have a really informative function and you add a constant to it, is you get that same really informative function, just shifted up. So you can still extract all of the details about the correlated structure of the metallicity within this galaxy, as if there was no noise there at all, which is awesome. And it works really well in simulated data. And it also works really well in real data too. So here it is on a real galaxy that we're getting from use. We're getting a lot of information about the spatial scales and the amount of variance within these models. A couple more words on it. This data is really informative. It gives the same amount of information that a power spectrum analysis does, and you can translate between results for both of them. But it's also nice in that it works on bad data. Power spectra have trouble dealing with missing pixels and strange edge effects that you see in galaxies. So this is the kind of like more natural applications of this kind of task specifically. So once you've got a semi-variogram for the galaxy, this then allows you to fit a model to it that lets you understand the nature of these small scale fluctuations. And so what I'm interested in is taking this observed data and comparing it to simulated data and theoretical data. And so the first project that I did as part of my PhD work was using this to test an analytical model of the metallicity distribution within galaxies. So this is a model from Cromwell's team. It's a set of stuff, stochastic partial differential equations that makes a few assumptions. But rather than go through the literal 100 equations that are in this model, I thought it'd be more fun to just put them in a simulation so we can see what's happening. So each of these yellow points that you're seeing appearing is a supernova going off, and then it's slowly diffusing its metals into the surrounding IgM just through linear diffusion. And so what you can see after you let it run for a little bit of time is you get this prediction for the spatial correlated structure of metallicity, which is something that we can then measure and test with our observations. So how does it look? At first glance, it seems like it's doing a really good job of replicating the data, until I tell you that the Cromwell-Ting model is not the red line, it's the green line. And I've had to scale it up by a constant factor to make it match what we see. So it's doing a pretty good job of like predicting the spatial extent of these metallicity correlations, but it's predicting that the power is much smaller than what we're seeing. In other words, the Cromwell-Ting model is unpredicting the variance by a factor of about 1,000. To show you that I'm not cherry picking, is the same result for 6 other galaxies. And in each case, I've had to scale it up by a factor of 1,000 to 10,000 to make it match the data. So the real takeaway is that galaxies are not very well mixed. They're highly inhomogeneous, and this inhomogeneity is a signature of the small-scale baryonic physics that we're trying to observe. So the first model I checked didn't work, so the next thing to do is check at some more detailed models. So with my master's student Tree, who I'm informally co-supervising, we're looking at analyzing the fire code, looking at some more advanced simulated galaxies, trying to get their semi-variograms. Early results, qualitatively, they look kind of similar for the largest galaxies. They're not really matching for the dwarves, and so a lot of more research to be done and kind of like seeing what's happening here. So another thing you can do with this kind of like modeling framework is use it to make predictions of the metallicities at places where you can't measure it directly. So this is a galaxy that was recently observed by the really high resolution Typhoon survey. But one problem with this survey is it's really low completeness. You can only get the metallicities at H2 regions, and you can't get it in any other parts of the galaxy where you have ionization or other dominating factors. So if you want to find the metallicity at some other point, the standard method is to use the metallicity gradient. And when you do that, you get a picture of your galaxy that looks like this. There's more metals on the middle, less metals on the outside, but there's a lot of data that's kind of like being lost when you do this process. On the other hand, when you take a geostatistical approach, you learn the shape of the small scale correlations within the data, and then you get a picture of your galaxy that looks like this. And so there's still more metal on the middle, there's still less metals on the outside, but all of a sudden you can see all these small scale features of like active, star formation and metal enrichment that hasn't been mixed in yet. All of these signatures of like these small scale physical processes that we're trying to understand. So to test this kind of like methodology, I'll go on.
Know that star formation doesn't happen uniformly across a galaxy, that it tends to be concentrated in spiral arms.
And you can
see a spiral arm, but of course
you can kind of see that here.
Out saying you don't have data there. But it seems like you're bound to fail on your first model.
Sorry, I don't quite understand the question.
Your first model, you had the supernovae going off
uniformly
over the galaxy. And you know that's not true.
Right. So that is a question, is how much of the correlation in the metallicities is due to correlation in star formation. Remains to be seen, I guess. But I think the main kind of like takeaway from that thing is that if you just assume linear diffusion of metals, you get something that's way too well mixed. And I think this would be the case even if you had star formation preferentially happening in certain regions. Maybe not if it's metal enriched star formation. Maybe that's a way to get around it. That's a theory that I'm kind of like looking at as well. But in summary, I agree. All right. So moving on. So these geostatistical models are great. To prove that they're good, I wanted to make some predictions of the metallicities at points that we had measured. So I trained each of these modeling procedures using 90% of the data, fit it to the rest of 10% data, and cycled through to get predictions for every different metallicity point that we observed. So when you do this with the metallicity gradient, you get a pretty good agreement between the model and the data, but you get a lot of regression to the mean. You tend to overestimate the metallicity of low metallicity points and underestimate the metallicity of high metallicity points. On the other hand, with this kind of geostatistical model, taking into account the small scale fluctuations within galaxies, we get a much better agreement between the data and the models, even for these low metallicity outliers, which is really promising. And some other work I'm working on with a master's student at the moment is trying to connect these metallicity maps to other properties of these star-forming galaxies that we have, such as their molecular gas density, using data of different resolutions as well, which is a lot of fun. Okay, another thing I did for this kind of like research is I got the question over and over in conferences of like, what resolution do we need in order to conduct one of these geostatistical analyses? So I started with a really nice Typhoon data set. I binned it and binned it and binned it and binned it all the way until we can get to things of like about a kiloparsec resolution, which is what we get for a lot of like these wide scale IFU surveys and a lot of simulations as well. So for each of these simulated data sets, or each of these constructed data cubes, I constructed the semi-variogram. So we can see a couple of features. Firstly, the variance decreases as you get to coarser resolutions. This makes sense just because you're averaging around regions. It's very predictable as well, which is nice. But once you get to kind of like beyond about 300 parsecs per pixel, we start seeing that some of these details on the small scale features of these varograms start getting a bit blurred out and a bit harder to recover. Another thing we looked at is how accurate our predictions are with these models when we go from low resolution to high resolution, low resolution to high resolution, sorry. So for the coarsest resolution maps, when we have about a kiloparsec per pixel, the geostatistical model doesn't really outperform the metallicity gradient model. But as we get to higher and higher resolutions, the performance of these geostatistical methods just increases and increases and increases. So all in all, what's the data that what resolution should we be looking at? The summary is about here. These all gave us consistent correlation scales when we used an MC fitting procedure, which is really good news because there's a lot of data that already exists in the literature that has resolutions of this or finer, which means that we can expand this geostatistical analysis to hundreds of galaxies with different masses, star formation rates, and other properties.
But does that not matter because they're not very early? Yeah.
Right, that's the question. So I've been looking at spirals so far, just because they're the nicest, most beautiful face-on data. But I'm keen to expand it to other morphologies as well. Got a few dwarf galaxies that I'm looking at as well. So yeah, keen to see if they're still chemically homogeneous in ellipticals. Yeah. Great. So now the next question you're probably asking is, well, what happens when we don't have this resolution? What happens when we have data that's not quite this fine, but we still want to be able to fit interesting models to it? Specifically, I'm talking about data that looks like this. So these are a bunch of galaxies at around cosmic noon with lens data. And you can see for all of them, they don't really follow the typical metallicity gradient model. They're highly clumpy, they're highly irregular, they're highly inverted. And this is kind of like signatures of small scale astrophysical processes that we're trying to understand as well. Specifically, to illustrate this, I constructed these 4 metallicity maps. All of them have the exact same metallicity gradient, but all of them show different small scale features. So this first one is indicative of smooth secular evolution without much going on. This second one has a signature of a recent merger between a low metallicity and high metallicity source. This third one has enrichment along the spiral arms. And this fourth one has an inefficient mixing component leading to this small scale structure as well. Another problem with just using the metallicity gradient method is that it tends to suffer from something called PSF smearing. So when you have a large point spread function, a metallicity gradient gets smeared out and it looks like a shallower point spread function. It's kind of like what we're seeing in this graph here. So to correct for both of these problems, I worked with a team to develop an extension to the popular software Lenstronomy, which is a forward modeling software. So basically how it works is you go from 2-dimensional predicted maps of the metallicity and flux distribution of the galaxy, and you can account for effects such as lensing, convolution by a PSF, pixelization, and also adding noise, giving you a product that you can then compare to real data in a kind of apples to apples way, which gives you insights into your 2-dimensional models that are underlying. And then you can iterate through this until you can converge on a solution. So first of all, this does a really good job of correcting for the point spread smearing function. So when you have the standard approach, basically what you find is as you get to poor resolution, the metallicity gradient that you measure diverges and becomes flatter from the true metallicity gradient. On the other hand, using the Lenstronomy software, we find a much better agreement between the recovered values and the true values, even when these PSFs become wide. Another application is that we can use it to fit this clumpy galaxies at higher redshift where we don't have a single component. So for example, for this one, we have 3 different components making up this light profile, and you can fit a separate metallicity to each of them, giving you a different way to kind of like model these galaxies that isn't just a metallicity gradient. And so this is ongoing work that I'm doing at the moment with the JWST glass collaboration. I'm waiting for some nice metallicity maps to come out of them so I can analyze them using this framework, see some 2-dimensional signatures of structure. So now, in the last part of the talk, I want to talk about what you can do to find signatures of chemical inhomogeneities in galaxies where you don't have resolution. And how can this be done? Basically, the trick is, usually when we measure the metallicity of a galaxy, we do this by taking all of the light of the galaxy and putting it into one big bucket and saying, all right, based on all of the light in this galaxy, what fraction came from elements heavier than helium and what fraction came from other gas? Another way to do it is instead, if we can take just a small patch of the galaxy and look at the light from that. So rather than using a bucket, now we're using an eyedropper to see what's the metallicity at this particular location of a galaxy. Now, if our galaxies are perfectly well mixed, these two things should agree. But if we have a galaxy that's chemically inhomogeneous, then these two things are not necessarily the same for all galaxies. So what can we use as our cosmic eyedropper? The answer is gamma ray bursts. So is everyone familiar with gamma ray bursts? All right, real quick, two things you need to know about them. One is that they're super bright. So it's all the energy of a supernova directed along one narrow beam. We can see them from up to basically any redshift where they're occurring. The second thing to know is that they're biased to low metallicity regions of star formation. So you need a low metallicity progenitor to be ordered to be spinning rapidly enough to generate a gamma ray burst on collapse. So now we've got these two kind of ways of sampling the ISM. We can look at the absorption signature from a gamma ray burst afterglow. I'll be calling this Z absorption. Or you can look at the emission spectra using light from the galaxy itself. I'll be calling this Z emission. So now we have two different ways to measure the ISM in these gamma ray burst host galaxies. The first question to ask is, do these two metallicity measurements on average agree? So to answer this, I turned to the illustrious TNG simulation, which is a large volume, high resolution suite of cosmological hydrodynamics with a full suite of baryonic physics, accounting for star formation, metal enrichment, all the key processes that you want to have in your models. So with this data, I took a bunch of different snapshots, looked at which galaxies would likely be gamma ray burst hosts based on how much metal poor gas they were forming, selected these gamma ray burst hosts and looked at the metallicities along the line of sight to an observer and also through the galaxy as a whole itself. So using this, I found that in general, the emission and absorption line metallicities of a galaxy are expected to disagree in a kind of nice, predictable way. For the lowest metallicity galaxies, generally the gamma ray burst absorption metallicity is pretty similar to the emission metallicity, just because all the gas will be at a low metallicity. But as you go to these higher metallicity sources, the metallicity of a gamma ray burst is biased to these low metallicity pockets of gas. So when you look at a sightline, it preferentially has a lower metallicity than the overall metallicity of the galaxy itself. Which is a pretty nice prediction, but that's just one simulation with its own choice of like parameters for the baryonic physics that's going on. And so the next thing that I wanted to do was look about how does this vary when we vary the parameters that we're putting into our models. So this is using 3 different simulations that are all trying to do the same thing, like get large scale populations of galaxies at a range of redshifts, but using slightly different ISM physical prescriptions to do it. And so doing the same process, selecting gamma ray burst hosts, looking at their absorption metallicity, comparing it to their emission metallicity, I found 3 different predictions for what the relationship between these two quantities should be. So qualitatively, they all kind of agree. Emission metallicities should be higher than absorption metallicities, but the actual shapes of these simulations are very different. So this one magenta data point that I'm showing here was the only gamma ray burst host at time of writing for which both absorption and emission metallicities had been measured. Fortunately, since then, there has been a James Webb program to follow up on 10 gamma ray burst hosts to get their emission metallicity. And when I put that data on the plot, it looks like this. So now there's kind of like enough data to almost start distinguishing between these two different models. And I haven't run the stats yet, but it looks like it most closely agrees with TNG, has a bit of tension with Eagle. So yeah, really exciting sign to start using the data that we have to start getting a handle on these subgrid physical methods. But yeah, this kind of like is showing that, at least from our simulations point of view, chemical inhomogeneities don't just exist in low metallicity local galaxies, they also exist up to higher redshifts, which has a lot of consequences for the formation of metal poor transients throughout the universe. And specifically, I've been interested in parent stability supernovae. So these are really bright supernovae that are rumored to come from the population 3 stars and other low metallicity stars. No one's ever seen one. And the reason for this is generally if you have like a low metallicity system, people expect it to be exclusively forming in these really high redshift, really low metallicity galaxies. But what I've shown in this research that I've done with Max Briel at the University of Geneva is when you account for these chemical variations within galaxies, you can have parent stability supernovae forming at much lower redshifts, which means that they're, in principle, probably a lot more observable. So to test this out, I've tried to calculate how many parent stability supernovae we'd be able to discover, both with HyperSuPrimeCam, which is a mission that ran from 2012 to 2016, and also with the recently launched Euclid Deep Survey. And so what I found with this one, when we account for the chemical inhomogeneities in galaxies with high Bessa prime cam over its 4-year lifetime, the number of parent stability supernovae we're expected to detect is 0.03, which is consistent with the 0 that we have detected so far. So good prediction. On the other hand, when we use Euclid over its lifetime, we expect 83 parent stability supernovae to be observed by this instrument, which is an order of magnitude than the 7 you would get if you assumed that these galaxies were chemically homogeneous everywhere. So yeah, bringing us to the summary, when you have really nice, really high resolution data, geostatistical methods are the way to go. You can get a lot of science out of your data this way. When you have data that's not as good, the lensastronomy module that I've developed for JOST applications is really good at fitting asymmetrical metallicity profiles to these galaxies. And finally, in the high redshift universe and beyond, we can use GRBs to detect metallicity inhomogeneities in galaxies, even when we don't have the resolution. So thank you very much. I'll take any questions. Yeah.
How does the diagram differ from just like a normal power spectrum? Is it like along straddle periodogram? Like the same time?
Let me answer this question with a bonus slide. So this is me with my friend Sabrina Berger, who's a colleague from University of Melbourne also, but she's more of a cosmologist. And so she's very familiar with the power spectrum. I'm very familiar with the semi-variogram. And we had a master student give a talk, and afterwards we just came together and argued for 2 hours about whether these were the same or different things.
Yeah.
One thing led to another, and we wrote this pedagogical piece together, which is basically a translation guide between power spectra, semi-variograms, and also the structure functions that are used by turbulence people as well. I don't know what a lone Scargill periodogram is off the top of my head, but we did make a glossary for this one, so it's probably in that. But yeah, I'd recommend this highly as a resource. We made it for grad students as well, so it's pretty accessible. Yeah.
I was wondering, like, with all of these different methods, how different is it from just using like a Fourier transform with proper windowing?
Yeah.
So.
Yeah. Yeah. And I mean, if you read this and have any thoughts about things we haven't included as well, let me know. Yeah.
I had a question related to the last part of your talk. I guess a similar question to what you're asking might be, how many GRBs do you see in galaxies which are high metallicity on average, right? Because see a lot is just in speed of beams. And I wondered if that might be, it needs to have slightly less data because you don't need to measure Z emission, Z absorption.
Right.
I don't know if anybody is considering that approach as well, or is it like.
No, I am. This is science that I cut, but my first project, my master's project, was literally about doing this. So motivated by the fact that we see low metallicity GRBs from high metallicity galaxies. There's kind of like 2 different explanations that we tested out. One was that galaxies don't have the same metallicity everywhere, or there's some metal-free path for gamma ray burst formation. And so we looked at statistics of like the rate of gamma ray bursts as a function of cosmic time, the masses of gamma ray burst hosts, the metallicities of gamma ray burst hosts measured in these 2 different ways, and looked at predictions from the illustrious data. And what we found was that when we accounted for all of this data with a chemically inhomogeneous galaxy model, all of the different surveys and statistics all agreed on a metallicity threshold of about 0.35 solar, which is similar to what the theoretical models had already predicted. So yeah, yeah. But then yeah, one of the things that kind of like came out of that was noticing that these 2 metallicity things were different, and their turnoff was roughly where the threshold for gamma ray burst formation is. So I don't know, it's kind of inspired by that earlier observational kind of like comparison.
Yeah, I think it's sort of like the parent stability supernova.
Yeah.
So I thought the predictions with Euclid were really, really neat, but I'm not too familiar with these. Like, if we do see these 83, will we know that we've seen it? Like, do they have very different observational signatures than other supernovae?
Yeah, right. That's the question. So a lot of people are kind of like nervous about that. Like, how do we tell them apart? One nice thing that I got with this paper is that in addition to just predicting the number, I'm predicting like the number versus redshift as well. So I can tell you what redshift they're most likely to be expected at. And also we used a bunch of different light curve models for these parent stability supernovae. Some of them are more visible than others. Some of them are more common than others. So we've also got rates of like what fraction of these parent stability supernovae that you observe are expected to have this light curve. So we know what the most common light curves are. We know what the most common redshifts are, which gives us some clues of like where to look or what to look for. But then actually extracting that from the data is a challenge, right? Yeah.
Explain why the gamma ray bursts go up in low metallicity environments. Is that a theoretical thing or an observed thing?
Both. Well, it's theorized and observed, but the reason is sort of like for a gamma ray burst to explode via the collapsar mechanism, you need a really high mass, really rapidly rotating star at the time of its death. The more metal-rich your star is, the stronger its stellar winds are, and so it'll lose more mass and angular momentum throughout its lifetime. And so it's a threshold based on like, you need a certain amount of mass and angular momentum at the end of your life to form a gamma ray burst. And then I'm just, the delay time for a gamma ray burst exploding and forming are pretty short. So I'm just saying the metallicity of the gamma ray burst is the metallicity of the gas.
Okay, so with this method, so you're getting effectively one absorption measurement, like one gas, resolved gas measurement, and then one integrated measurement. So like, in terms of like what it's telling you physically, if these things are offset from each other, like what does that tell you physically? Like, because like, there can be a lot of different ways that it's mixed, right? Like, so what is kind of the like theoretical that?
I mean, the easiest answer that I can get is sort of like, I don't know, it's a statistic that you can measure. The more close your galaxies are to homogeneity, the more close this will be to a one-to-one line. And so it tells you about the degree of chemical inhomogeneity in your galaxy. Not in a way that's directly translatable, I think, to something nice and theoretical, but it is observable. So
Here, there's no more questions, we just say applause, right?
That's right.
Thank you for a great talk.